Have you ever really stopped to think about just how much stuff is packed into our devices? I mean, the density. Imagine this. Every single photo you took, say, over the whole last year, now picture all of them fitting comfortably into the space of one single dot of ink. From a regular ballpoint pen. Sounds completely wild, right? Almost sci-fi. But that's roughly how compact data storage is inside a hard disk drive, an HDD. Welcome to TechDaily.ai. Today, we're doing a deep dive into that incredible hidden world. But before we metaphorically crack open that hard drive, just a quick word from our sponsor. This deep dive is brought to you by Stonefly. They're your trusted solution provider and advisor for all things enterprise storage, backup, disaster recovery, hyper-converged solutions like VMware, Hyper-V, and Proxmox clusters, AI servers too, SA365, which is a turnkey security appliance, and also public and private cloud solutions. You can find out more and really empower your data strategy over at stonefly.com. Definitely check them out. Okay, so the big question we're tackling today is, how on earth does something like, say, an entire library's worth of books fit onto one tiny little metal disk and stay there reliably for years? Our mission, then, in this deep dive is to really pull back the curtain on the hard disk drive. We'll look at its fascinating components, reveal how data gets precisely stored and read using, well, invisible magnetic fields, and then we'll explore some of the really cutting-edge advancements that are constantly pushing the boundaries of data storage. We're going to uncover the, frankly, incredible engineering that makes so much of our digital lives possible. All right, let's get into it. Let's peel back that, that unassuming metal casing and see what's inside. Most of us just see a box, right? But what's really going on in there?
Yeah, it really is a whole different world once you look past the cover. It's incredibly intricate.
Yeah.
Right at the heart of it, naturally, is the disk itself, or platter, as it's often called. That's where all your data actually resides. And modern drives, they often have several platters stacked up. Each disk is typically made from an aluminum-magnesium alloy. But the really functional part, the layer doing all the heavy lifting for your data, it's incredibly thin, just 120 nanometers.
120 nanometers, that's unbelievably thin.
It is, and it's made of a special alloy, cobalt chromium tantalum. Now, the genius bit here is that this super thin layer contains tiny, tiny magnetic regions or domains, think of them like microscopic magnets, and their magnetic direction, north or south pole, pointing up or down, let's say, can be flipped, manipulated with extraordinary precision. And that manipulation, that's fundamentally how we encode information, your ones and E's. Now, these platters, they don't just sit there, they're mounted on a central spindle. And that spindle spins, thanks to a brushless DC motor built right into it, at a really remarkable speed, typically 7,200 revolutions per minute, RPM.
Whoa, 7,200 RPM. That's spinning incredibly fast.
So what's actually interacting with that disk, spinning away like that?
That would be the head stack assembly. And it's not just one arm, it's usually a comb-like structure with arms extending out. There's one arm positioned just above and one just below each surface of each platter. And right at the very tip of each arm, there's a small component called a slider. And mounted on that is the crucial part, a tiny read-write head. Honestly, this whole assembly, it's one of the most amazing pieces of mechanical engineering inside the drive.
Okay, so what makes it so amazing? Does it actually touch the disk? Because like you said, 7,200 RPM, that sounds like a recipe for instant disaster if they touched.
But that's the clever part. It's precisely because of that high speed that it works so well. It doesn't touch. The slider, the little piece holding the head, it has this really ingenious aerodynamic shape. As the disk spins really fast, it creates this incredibly thin cushion of air right above the surface, like air hockey almost.
An air cushion generated by the spinning. Exactly. And the slider is designed to, catch this airflow. It effectively rides on that air cushion. This causes the read-write head to float, or the technical term is fly, incredibly close to the disk surface. We're talking a distance of just 15 nanometers.
15 nanometers. I can't even picture how small that is.
It's ridiculously small. To give you some perspective, that's only about maybe 100 atoms thick. Compare that to, say, a sheet of aluminum foil or even a human hair. It's vastly, vastly thinner. This flying is absolutely key. It prevents any wear and tear and allows for that incredible precision needed to read and write data. And that's also why the ARM assembly only moves out over the data area of the disk after the platters have spun up to full speed. When the drive powers down or isn't spinning, the ARM assembly is safely moved or parked off to the side, usually resting on a little plastic ramp.
So it parks itself for safety. Makes sense.
Precisely. It prevents any accidental contact, any potential scratching or damage to either the head or the delicate magnetic surface of the platter.
That kind of precision, though.
Yeah.
Landing something that delicate, just atoms away from a surface, spinning that fast. It's just astounding. How do they possibly control the movement of that arm with such, well, pinpoint accuracy?
Yeah, the control system is another marvel. It uses something called a voice coil motor. You might have heard the term. It's similar in principle to how a loudspeaker works. Essentially, you have a coil of wire attached to the back end of the head stack assembly. This coil sits within the field of some very strong permanent magnets, typically neodymium magnets.
Okay.
Now, when you pass an electric current through that coil, it generates its own magnetic field. It becomes an electromagnet, right? And the interaction between the coil's field and the permanent magnet's field creates a force. That force pushes or pulls the entire arm stack assembly, causing it to pivot and sweep the read-write heads across the surface of the platters. And if you reverse the direction of the current, you reverse the direction of the force. Simple as that, but incredibly effective.
And fast, I imagine.
Very fast and incredibly precise. This voice coil motor system allows the drive's electronics to control the exact position of the read-write head over the correct track with an accuracy down to about 30 nanometers. It's phenomenal. Plus, because the arm assembly is designed to be very lightweight, this powerful motor can whip it back and forth across the different tracks on the platter up to maybe 20 times per second, making these incredibly rapid, tiny adjustments to follow the data tracks accurately. All the signals, the data being read or the signals telling the head what to write, they travel through a very thin, flexible ribbon cable, like a flat plastic strip with wires embedded. That connects the moving head assembly down to the main control board.
Right, the printed circuit board, the PCB, that's really the brains of the whole operation, isn't it? Tying all these amazing mechanical parts together and making them work.
Absolutely. The PCB is the control center. It houses the main processor, the chip that orchestrates everything happening inside the drive. It's like the conductor for this tiny high-speed orchestra. You'll also find a DRAM chip on there. This acts as a sort of super fast scratch pad memory for the processor and also as a temporary holding area. A buffer for data that's coming in from the computer or waiting to be written to the disk or data that's just been read.
A buffer, okay.
Yep. And then there are other specialized chips too, one dedicated to precisely controlling that voice coil motor we talked about, managing the arm's position, and another chip to manage the speed of the spindle motor, keeping that 7,200 RPM perfectly constant. And of course, on the outside edge of the PCB, you have the connectors. The standard SATA connector, that's for data communication back and forth with your computer's motherboard, and a separate connector just for supplying power to the drive.
So much complex electronics and mechanics packed into such a small space. A device we often just plug in and completely forget is even there. What about protecting this, this delicate inner world from the outside environment? Dust, particles.
Ah, yes, protection is absolutely crucial. Given how close that head flies to the platter, there's a very carefully designed rubber gasket that runs around the edge where the metal casing meets the base. This creates an airtight seal, keeping the internal environment clean. And inside, there are actually two filters. One is a recirculating filter that continuously catches any microscopic particles that might somehow be generated internally over time. The other is a breather filter, sometimes called a barometric filter. It allows the internal air pressure to equalize slowly with the outside ambient pressure, but it filters that tiny amount of air exchange extremely effectively.
Filters, right. Why are they so critical?
Well, think back to that 15 nanometer flying height. A single tiny speck of dust, which might seem invisible to us, can easily be, say, 5,000 or even 10,000 nanometers across.
Whoa, much bigger than the gap.
Massively bigger. So imagine that dust particle hitting the spinning disk surface at 7,200 RPM, remember, and then the read-write head crashing into it. It's called a head crash, and it would be catastrophic. It would destroy the head, gouge the platter surface, and cause immediate data loss. That's why these drives are assembled in ultra-clean room environments, much cleaner than even a hospital operating room. And it's why you should never, ever try to open up a hard drive yourself outside of such an environment. You'd instantly contaminate it and likely ruin it.
Definitely noted. Okay, so we've kind of dissected the physical components now, but the real magic, the answer to how does a library fit on a disk, comes from how all these parts work together, how they dance maybe, to store and retrieve information. How does all this physical engineering actually translate into digital data?
Right. It's all about incredibly precise organization and that magnetic layer. Think of the surface of each platter, that cobalt alloy layer, almost like a minutely ruled notebook page. But instead of lines, it's logically divided into literally hundreds of thousands of concentric circles. These are called tracks.
Concentric circles, like on a vinyl record, but way, way more of them.
Exactly like that, but yes, vastly more dense. A modern drive can easily have over 500 1,000 tracks on just one side of one platter. It's hard to even conceive. And then each of these incredibly narrow tracks is further divided into smaller segments called sectors. A sector is typically the smallest unit of data that the drive reads or writes at one time. And each sector isn't just raw data, it has a very specific internal structure, which is vital for making sure everything works reliably.
Structure within the sector, what does that look like?
Well, first, there's usually a preamble or a synchronization zone. This basically tells the read-write head, okay, here comes data, and helps it lock on to the exact speed the disk is spinning at right beneath it and know how long each individual bit should be. Then there's an address part. This contains information that tells the head precisely which track it's currently over and which sector number is about to pass underneath it. So the drive always knows exactly where it is. After the address, you get the actual user data itself. This is where your files, your photos, your documents are actually stored. Typically, this data block is 4 kilobytes or 40 out of 96 bytes in modern drives. Following the data, there's a really important section, the error correcting kind, or ECC. This is like a very sophisticated checksum or parity check. It allows the drive controller to verify that the data just read is accurate and even correct minor errors on the fly if a few bits got corrupted somehow.
Like a built-in spell check for data.
That's a great way to put it, yes. And finally, there's usually a small gap at the end of the sector. This provides a little bit of timing tolerance, a buffer zone, especially important during the writing process to make sure writing one sector doesn't accidentally bleed over and corrupt the start of the next one.
Wow, that's incredibly organized. So, okay, let's zoom in on the core process. How do they actually write the data? How do they make those ones and zeros stick onto that magnetic layer?
It all comes back to those tiny magnetic domains we talked about in the cobalt, chromium, tantalum layer. Writing data is essentially the process of using the write head to force a specific localized region, a single domain, to become magnetized in one of two opposite directions. Think of it as forcing the tiny atomic magnets within that domain to all point their north poles either up or down relative to the disk surface. One direction represents a binary 1, and the opposite direction represents a binary 0.
And how small are these domains we're talking about?
They're incredibly tiny. On a modern drive, a single magnetic domain storing one bit might be roughly, say, 90 nanometers wide by maybe 100 nanometers long, and using the full 125 nanometer thickness of that magnetic layer we mentioned earlier, just minuscule. So when the drive needs to write a bit, the circuitry sends a pulse of electric current through a tiny coil of wire located in the right part of the read-write head. This current creates a very strong but also very localized magnetic field right at the tip of the write head.
This magnetic field is strong enough to jump across that tiny 15-nanometer air gap between the flying head and the disk surface. And when it reaches the platter, its force overcomes the existing magnetic orientation of the domain directly underneath it, forcing all the atoms within that domain to align their magnetic fields in the desired direction, either up or down. This effectively turns that tiny domain into a miniature permanent magnet, storing that single bit of information. And the really amazing part, because of the material properties, once that external field from the write head moves away as the disk spins, that magnetic orientation is retained. It stays magnetized in that direction for years and years, holding your data securely.
That's the permanent part of permanent storage. It just holds that magnetic state.
Okay, so we've written the data. We've got these tiny domains magnetized up or down. Now, how do we get that information back? You mentioned earlier it's not quite as simple as just detecting up or down. That's fascinating. What's the trick?
Exactly. It's a bit more nuanced than just sensing the static direction of a single domain. The read head is actually designed to be sensitive to changes in magnetic orientation, specifically the transitions between adjacent domains.
Changes. Why changes?
Well, it turns out that the magnetic field lines emanating from the boundary, where one domain pointing up meets another pointing down, or vice versa, create a much stronger, more easily detectable magnetic flux leakage above the disk surface compared to the field from a region where all domains are pointing the same way. So the drive's read system interprets these transitions. Typically, each time the read head detects a flip, a change in magnetic orientation from one domain to the next one passing underneath it, that event is assigned a binary 1. If the read head passes from one domain to the next and there's no change in orientation, say both are pointing up or both are down, that absence of a transition is assigned a binary leave.
Ah, okay. So a flip is a 1, no flip is a 0.
Precisely. So for instance, if you wanted to store the binary sequence, let's say 0011, 001, 01, The right head would arrange the magnetic domains like down, 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 down. You see the flips. No flip 0, no flip 0, then a flip from down to up 1, no flip 1, flip from up to down 0, no flip from down to up 1, no flip 0. Oh, wait, I might have miscounted the example there. Let me rephrase. Let's take 0, 0, 1, 0, 0, 0 here. The transitions define the ones. So you might have down, down 0, down, up 1, up, down 0, and down, up 0, down, up 0, down, up 1, up, down 0. The 1 marks the spot where the magnetic field flips direction relative to the previous bit.
Got it. The change itself is the signal for a 1.
Exactly. And how does the read head actually detect that change? That relies on a really clever bit of physics and material science called giant magnetoresistance, or GMR.
Giant magnetoresistance.
Oh, wow.
Sounds impressive.
It really was a breakthrough Nobel Prize-winning technology, actually. In simple terms, a GMR sensor is made of multiple extremely thin layers of conductive magnetic materials. The key property is that its electrical resistance, how much it resists the flow of electric current, changes significantly depending on the strength and orientation of an external magnetic field passing through it.
Okay, so resistance changes with magnetism. How does that read the data?
Well, when the GMR read head flies over a boundary between domains where the magnetic orientation flips, it encounters that strong magnetic flux leakage we talked about. This strong field causes the resistance of the GMR sensor to drop significantly. The drive electronics detect this drop in resistance and interpret it as a 1.
Low resistance means a 1.
Right. Conversely, when the head flies over a region where there's no transition, no strong magnetic flux, the GMR material's resistance stays high. The electronics see this high resistance and interpret it as a 0 wind. It's an incredibly sensitive way to detect those tiny magnetic changes. And remember that preamble at the start of each sector. That helps calibrate the read sensitivity and timing, and the ECC code at the end. That ensures data integrity, helping sort out any ambiguities, like, say, a long string of identical bits, all zeros where there are no transitions for a while.
It really is an astounding combination of physics, material science, and precision engineering all working together.
Yeah.
But, the story doesn't just stop there, does it? Hard drive technology hasn't stood still. It's kept getting better, especially in packing more and more data in. That term areal density, right? How much data fits in a given area? What's the scale of progress been like?
Oh, the progress has been absolutely staggering. Mind-blowing, really. If you look back over the last, say, 60 years of hard drive development, the areal density, the number of bits you can squeeze onto a square inch of platter surface, has increased by a factor of over 50 million.
50 million times denser.
Yes. And perhaps even more impactful for us as users is the cost. The cost to store a given amount of data, say trillions of bits, has plummeted even more dramatically. It's dropped by a factor of over 100 million in that same period. To put that in perspective, think about this. If you could somehow take a modern, high-capacity hard drive back in time to the 1960s, based on the cost per bit back then, its value would be estimated at over $4 billion.
$4 billion? For a drive that costs?
Exactly. A drive that today might cost you less than $40 and is vastly superior in every way, faster, more reliable, smaller. It's just a phenomenal illustration of relentless technological innovation, driven by finding ways to make those magnetic domains smaller and pack them closer together.
Okay, that's incredible progress. So what were some of the key breakthroughs, the big leaps forward, that allowed engineers to keep shrinking those domains and boosting that density?
Well, one major shift happened around maybe 2010 or so. It's called perpendicular magnetic recording, or PMR.
Perpendicular, as opposed to what?
As opposed to longitudinal or horizontal. For decades before PMR, the magnetic domains were oriented lying flat, parallel to the disk surface. PMR literally stood them up on end, so they're oriented vertically, perpendicular to the disk surface.
Why the change? What does standing them up achieve?
It comes down to physics and stability, especially as things get smaller. As you shrink magnetic domains, they become more susceptible to being randomly flipped by thermal energy, just the ambient heat. This is called the superparamagnetic limit, and it sets a fundamental barrier to how small you can make traditional horizontally recorded bits. By orienting the domains vertically, PMR allows them to utilize the depth or thickness of the magnetic recording layer for stability, rather than just the surface area. This makes the bits more magnetically stable even when they are made much smaller in terms of their footprint on the disk surface. It was a crucial step to break past density limits.
Makes sense using the third dimension. What came next?
The next major step, which started becoming commercially widespread around 2020, is shingled magnetic recording, or SMR.
Shingle, like shingles on a roof.
Exactly like that. That's the perfect analogy. In traditional recording, often called CMR or conventional magnetic recording now, each data track was written distinctly, with a small unused space, a guard band, between adjacent tracks to prevent interference. SMR gets rid of those guard bands to pack tracks closer together. It does this by writing new tracks so that they partially overlap the previously written track, just like laying shingles. You write a track, then the next track slightly overlaps it, the next one overlaps that, and so on.
But if they overlap, how can you read just one track back without getting interference from the one on top of it?
Ah, that's the clever part. The write head needs to be relatively wide to generate a strong enough magnetic field to write the data reliably, but the read head can be made much, much narrower than the write head. So even though the tracks are written overlapping like shingles, the narrow read head can still read back the data from the exposed, non-overlapped portion of each track without being significantly affected by the adjacent overlapping tracks. It allows for a significant increase in track density and therefore overall capacity.
That sounds incredibly clever. Squeezing even more in.
What?
I sense a but coming. With all these advancements, surely there must be some kind of trade-off. Does something this intricate, like SMR, have any downsides?
That's a very perceptive question, and yes, SMR does come with a notable performance characteristic, let's call it, a trade-off for that higher density. The issue arises when you need to rewrite data that's located on one of those underlying partially overlapped tracks. If the data on the track, or tracks shingled on top of it, is still valid and needs to be kept, the drive can't just simply overwrite the lower track.
Why not?
Because the wider write head would inevitably overwrite and destroy the valid data on the overlapping portion of the track above it. So what the SMR drive has to do in this situation is perform a kind of read-modify-write sequence. First, it has to read the valid data from the overlapping upper track, or tracks, and temporarily store it in that DRAM buffer cache we mentioned earlier. Then it can finally write the new data to the desired lower track. And immediately after that, it has to write the previously saved valid data back onto the upper track.
So it's doing a lot more work just to rewrite one block of data sometimes.
Exactly. This sequence of reading the old overlapping data, writing the new data, and then writing the old data back again take significantly longer than a simple overwrite on a non-shingled CMR drive. This means that for workloads involving a lot of random writes or frequent rewriting of existing data, SMR drives can sometimes exhibit noticeably lower performance. It's a density versus write performance trade-off.
Good to know. So PMR, SMR, what's on the horizon? What's the next big thing people are working on?
Well, the technology that's really seen as the next major step, though it's taking a while to become commercially mainstream, is heat-assisted magnetic recording, or AMR.
Heat-assisted. You're adding heat to the process now.
Yes, in a very, very controlled way. HAMR technology integrates a tiny laser diode onto the write head assembly. This laser fires a minuscule, highly focused boom to momentarily heat a tiny spot on the disk surface, the exact spot that's about to be written, to a very high temperature, maybe hundreds of degrees Celsius, but just for a nanosecond.
Wow. Why heat it up? Wouldn't that risk damaging the data or the disk?
It sounds counterintuitive, but the heating is incredibly brief and localized. The reason for doing it is related back to that stability issue we discussed with PMR. To keep increasing density, we need to use magnetic materials that are extremely stable at room temperature, meaning they hold their magnetic orientation very strongly. They have high coercivity. The problem is these super stable materials are also very difficult to magnetize the write head's magnetic field, which is already tiny, struggles to flip their orientation.
So the heat makes them easier to write.
Precisely. Heating the material temporarily lowers its coercivity, making it much easier for the write head's magnetic field to overcome its resistance and set the magnetic direction for the bit being written. Then, as the spot instantly cools back down after the laser passes, its high coercivity locks that written orientation firmly in place. This technique allows engineers to use these incredibly stable new materials, which in turn allows them to shrink the magnetic domains even further, potentially leading to massive increases in areal density beyond what PMR and SMR can achieve. It's complex, but very promising.
HAMR, another amazing bit of engineering.
Yeah.
You know, listening to all this, it really raises an important question, I think. Why does all this incredible microscopic detail matter to you, our listener, tuning in today, beyond just, the sheer technical coolness of it all?
That's a great point to bring up. I think firstly, it really highlights the sheer ingenuity, the incredible level of microscopic engineering and precision manufacturing that goes into these devices we rely on every single day, often without giving them a second thought. From that read-write head flying just atoms above a disk spinning faster than a car engine, to manipulating the magnetic state of atomic domains. It's truly a hidden symphony of physics and engineering, enabling our digital lives. Understanding even a little of it, I think, fosters a real appreciation for the technology around us.
That's certainly true for me after this conversation.
And secondly, on a more practical level, the continuous innovation in hard disk drives, even with the rise of solid-state drives, SSDs, remains absolutely crucial for global data storage. HDDs still offer, by far, the most cost-effective way to store truly massive amounts of data. Think about the huge data centers that power cloud services, streaming platforms, scientific research. They rely heavily on high-capacity hard drives. So this ongoing push for greater density and lower costs per gigabyte directly influences everything from the affordability of cloud storage to the capacity available on your own personal computer or network storage to the ability of businesses and researchers to handle ever-growing data sets. It's a powerful ongoing testament to sustained technological progress that really does impact your ability to store, access, and create digital information every day.
What an incredible journey we've taken today, really diving deep into the seemingly humble hard drive. We've uncovered some truly astounding insights along the way. From understanding how those impossibly tiny magnetic domains hold our precious photos and files, to picturing the precise, almost balletic dance of the read-write head floating just atoms away from that rapidly spinning platter, and learning about the relentless drive for more compact, more affordable storage through technologies like PMR, SMR, and looking towards HAMR. It really is a hidden marvel of engineering in plain sight.
It absolutely is. And perhaps that leads us to a final, maybe provocative thought for you to consider. The hard drive, as complex and ingenious as it is just one example, really, of the countless hidden engineering marvels that underpin our modern digital world. What other everyday technologies do you interact with, maybe take completely for granted, that might hold similarly fascinating secrets, similar stories of incredible innovation waiting to be uncovered if you just looked a little closer? Think about the constant, often unseen innovation happening all around us that truly shapes our daily lives in ways we rarely pause to appreciate. What else is out there?